Good afternoon, Uma and Shweta.
Good afternoon, Archana More, madam. Can you hear me?
Yes, I can. Are you able to hear me?
We'll start our session sharp at 3 o'clock, madam.
Yeah, okay, that is fine. You
Thank
are
you.
able to hear me, right? Are you able to hear me, Shweta?
Yes, ma'am, we can hear
Yes,
you.
madam, we
Okay,
can hear
okay,
you.
okay, that is fine.
Madam, I just made you co-host so that you can share the screen.
Yeah. So tomorrow is the last day for your conference, right? Shweta, how many students are attending this? Yes, Uma.
Hello.
Yeah, Uma. Yeah, I'm able to hear you.
Number of students is 15 to 20, like that.
Okay, okay. Are they BSc, MSc student?
Hello.
Yeah, yeah, I'm able to hear you. So are they BSc students or MSc students?
Mostly MSc. BSc
Okay.
is still classes going on like that.
Okay, okay, MSc student. No, I just want to keep my talk at that level. That's why I'm just asking.
Okay, okay, okay. Hello. Hello, Archana.
Yes.
Some are watching in the lab also on the big screen. So it's not seen, okay? How many are attending like that?
Oh,
Some,
no need. I mean, I just asked you, like, what is the background? It is a BSc background or
The
MSc?
background is MSc.
Yeah, that's what I need to know. Not exactly how many are attending. No.
Yeah.
Okay, yeah. Shall I start or what is the, yeah?
I'm just waiting for Shweta to come and
Okay.
start the session.
Yeah, no problem.
She is in the lab.
Okay, no problem. How are you doing? Is it
Okay.
your semester
She
is
is
still
just
going?
coming.
Okay.
Hello.
Yeah.
Good afternoon, everyone. I welcome you all for the 5th day of 1 week online international E-Symposium on modern mathematics. This celebrates Maria Mirza Khani's birth anniversary. Now I call upon Harita to introduce today's speaker, Archana More Madam, to you all.
Good afternoon, ma'am. Ma'am, am I audible?
Yes, we can hear you, Harita.
Thank you. Good afternoon to one and all. I, D. Harita, Assistant Professor, Department of Mathematics and Statistics, RBVR Women's College. It gives me immense pleasure to introduce the resource person of today's session, Archana Moriaman. Madam is an Assistant Professor at University of Hyderabad, Telangana. And Madam completed her PhD in mathematics from Harishchandra Research Institute under the Department of Atomic Energy, Government of India, Allahabad. Madam completed her master's in pure mathematics from Indian Institute of Technology, Mumbai. Madam research areas include algebraic geometry, mainly vector bundles. Madam worked as a visiting scientist at Chennai Mathematical Institute, Chennai. Currently, two people pursuing PhD under the guidance of Madam. Madam has conducted workshops for the Mathematics Olympiad students. Madam research areas are already we discussed as a vector bundles. Today we are going to listen to her lecture on this topic only. And Madam has published her papers in various notified national and international journals. She also authored chapters in 2 books, that is the Sear-Swan Theorem for Ring Space Analytics and Algebraic Geometry, Springer, Singapore, Analytics and Algebraic Geometry. Madam also published articles on the topic, the folding mathematics, in the special issue of the Proceeding of Telangana Academy of Sciences in the year 2020. Madam has also organized workshops and seminars, conferences at national and international level. She also delivered talks in various national and international conferences, seminars. Madam conducted series of lectures in workshops, to name few, Annual Foundation School CEMS Almora Uttarankhand and at Shivnadar University on differential topology, to name few. She also conducted orientation programs for teachers in several districts of Telangana and outside Telangana also. Apart from this research and her areas of interest, Madam also conduct outreach activities at Jawahar Navodaya Vidyalaya, Rangareddy district. She conducted 4 days workshop on problem solving strategies, and also she is an ROM regional coordinator for Telangana region. With this brief introduction, I welcome Madam to take over the session. Thank you, ma'am, for giving me this opportunity.
Thank you very much for the kind introduction, Harita. Shall I start my session? Shall I start my lecture now?
Please start, Archana Madam. Please start.
Yeah, okay, thanks, sir. Thanks Shweta and Uma for inviting me for this E-Symposium and Harita for introduction. Today's my topic is about vector bundle. This word algebraic, I wrote it. It is not very, it is just a vague term. I'll let you know. And what is the theme of, I decided to keep this lecture to talk about duality between algebra and that of a geometry. So that is main thing, how algebra helps geometry to solve some problems and how geometry enrich algebra. So that is essentially the theme. And I'll give some examples how vector bundles are essentially related into the central theme of duality between algebra and geometry. So let us, since we are having a student from MSc level also, I want to start my lecture very simply by reviewing what algebra and geometry we learned in schooling and graduation level, and then later on how we do research in the various areas of mathematics. I'll come to that. So I'll begin my session now. Are you able to hear me, Shweta, or shall I increase my voice? Is this okay?
Hello, we are able to hear.
Okay, good.
Only slightly higher volume would help.
Okay. I'll talk loudly. Yeah. Okay. Yeah. So as I said, let us first review what in algebra we learn, and then slowly we'll go to a geometric part, what we already know, and then we will see how we are use this knowledge into our further research. So we start with a number system. I don't want to go much into the details, but like in a schooling, we first start with the natural numbers, then we slowly learn negative numbers, and then rational, real, and complex subsequently. And a very long period of time in schooling, you learn these polynomials. And in polynomials, what we learn usually is the factorization of a polynomial, right? I mean, we spend significant amount of time dealing with the factorization of polynomials. And these polynomials, if you look at, they are over mainly over integers and sometimes over reals and so on. So what we mean by polynomials is these are the equations of the form, say 2x square plus 12x, something like that. I mean, any of these kind of polynomial we deal with. So these are actually over the integers, but also we can talk about the polynomials over reals or over the complex numbers as well. So for example, if I take up this polynomial, this is over the complex number. It is a degree 1 polynomial. And this complex polynomial we learn little later, but most of the schooling we deal with polynomials over rationals and real numbers. And another aspect of polynomials is finding roots. So we learn a lot of formulas. So for instance, in case of quadratic polynomial, we know how to find the quadratic polynomial using discriminants. So that's what we learn in our schooling. So these polynomial rings, we will come back again, how actually polynomial rings are very helpful in learning geometric aspect. And as you go ahead, what happens in algebra, abstractions keep on increasing. At a certain stage in your graduation, rather than studying sets, we try to study properties. So what do you mean by properties is, for example, what we study in our graduation is the linear algebra. So what is a linear algebra? This is a study of vector spaces. So we study what are Rns. For example, even complex plane, this is like a two-dimensional real plane. These kind of thing we learn during our in linear algebra. So now what we do is we are no longer concentrating on just like, for example, if you look at these polynomials, they are also these complex numbers. Earlier we can just look at them as a complex numbers or real as a real, but later on in linear algebra we study them as a line or as a plane inside R2, two-dimensional plane inside R2. Then further abstraction increases when we introduce something called a group theory. So what is a group theory is? It is a study of groups. And if you look at, for example, these integers, Under addition, this is a group that all of us know. So what is a group is? Group is a binary operation where we have a zero element is also there and an inverse is there. So for example, integers, now we study it as a group addition. Or if you look at real numbers, minus, if you remove zero from there, then this set is also a multiplicative group under this multiplication. Or if you look at a matrices, you can actually add two matrices and you subtract two matrices. So this is also a group. So now what we do is we study abstractly what is the definition of group. We study various properties of those groups, and then we conclude something about the given set, which is no longer a case in a school. In school, what happens is we concentrate on particular set and we try to study all the properties into that set. Similar to group theory, there is something called ring theory, where actually we study our rings. And what are rings are? Rings are instead of binary one operation, we will have a two operation. One is addition, another is multiplication. Or we study these polynomials, not like earlier to find a factorization and so on. We study them as a ring. So what do you mean? What is this polynomial as a ring? Is you can add two polynomials, you can multiply those two polynomials. So so once you study all these things abstractly, we don't need to individually work on the individual example. We can actually study them as a group, as a property. Similarly, in field theory, you must be learning these field extensions and so on. So that is how algebra is growing. Algebra abstractions keep on increasing in our algebra when we study algebra during graduation. Now let us see what happens in the geometric setting. In that geometry, what you do. So in the schooling geometry, what we learn is that we learn Euclidean geometry, rulers and compasses. So what is the Euclidean geometry? In that we study a lot of shapes. If you take a triangle, circles are the main thing. And then we look at this tangent to the circle and we study a lot of properties. Like if you join the center and any point on the tangent, then it becomes this perpendicular. And we learn a lot of theorems. Or we study these rulers and compass construction, where we learn how to bisect an angle and so on. So these kind of studies, we do it in our geometry. And as you go further, as we learn more and more geometry, we start learning what is the integration and the differentiation. So integration and differentiation is a part of a geometry because it gives you some kind of understanding about the shape. Like for example, what is integration is? Integration is area under the curve. So it is something to do with the geometry of your curve and the shape of your curve. So that is what we learn in our geometry. And as you go to the graduation and post-graduation, what we do is we change this integration and differentiation, which was earlier restricted to the reals, to the calculus, and where actually we start studying 2D geometry and the 3D geometry. So this line will be converted into surfaces, then the circle, this disk will be converted into the solid surfaces and so on. And rather than just looking at the area under the curve, we started studying surface area. We started calculating volume and so on using integration. So as you go older, as you learn more and more in geometry, what happens is dimensions keep on increasing, and as dimension increases, complexity also increases. So for example, here also you can look at, in fact, yesterday's class also, Professor Arvinda was talking about the torus, which is surface in this 3 dimension. So where actually we take a one circle like this, and another which rotate around the second circle, and we get a surface which is formed by the revolution of this smaller circle into the bigger circle. Or the cylinder, where again this is also an example of surface, or a sphere, this is also example of surfaces. And these kind of or if you take fill in this all these surfaces, then what you get, it is a volume. And you, as you go older, we start studying this geometric object. So now if you look at this transition or whatever you are learning from your graduation as algebra and geometry, what happens is we study this algebra and geometry separately. So what happens is we study this algebra and geometry separately throughout our until our graduation. So now we can ask our question to us whether can we study algebra and geometry parallelly. So that means not intersecting, just learn algebra separately and just learn a geometry separately. So can we study it like this, and can we do the derive the results which are good result just using algebra and just using geometry? And of course answer to this question is a false, and I want to give you some examples of why the answer to, I mean, why this statement is not correct, that we cannot go on like this to study algebra and geometry separately. So let us see some examples why we cannot do this. Okay. So for this, actually, I chose an example of a circle and a sphere, which is a very nice geometric object, which we study it right from the schooling till end. So let us actually review what happens in the study of circles. Okay. So what is a circle is? So if you know what is circle is, it is actually a set of so circle is lies inside the R2 plane, where we take a x comma y, and these are the elements, these are the points into this xy plane where x square plus y square is equal to 1. So the locus of this this equation x square plus y square is equal to 1. So this is what is actually our this is the locus of this set. Okay. So this is a very nice symmetric object, which is a circle, which we keep on studying. And as I said, tangent lines are also important. So let us see what is the tangent line to this circle at a point E. Okay, so what is the tangent? So what is the tangent line to a circle at a point is it is all those vectors which are so what are those actually? So if this my point AB, so all the vectors which are perpendicular to this vector from origin 0 0 to AB, that line, if you consider, that is a tangent line, right? So that means we are looking at this vector u comma v belongs to R2 such that AB plus BB is equal to 0. That means this is A comma B is perpendicular to UV. So here A and B, this is a known quantity, and UV are variables. So we are looking at them. So it is this is a line which is perpendicular to a vector AB. Okay, so this is a tangent. Now, so this is happening inside a two-dimensional, and then let us look at actually what is the three-dimensional circle, or what we call it as a sphere. Okay. So in three-dimensional sphere, where it lies, actually it lies inside R3. Okay. So though it is a two-dimensional object, it is embedded inside R3 plane, and you look at all those points x comma y comma z such that x square plus y square plus z square is equal to 1. This is our equation. Okay. So if you look at this here, this is a xyz plane, and we can look at this sphere, which is unit sphere I'm looking at. So radius 1 and origin at a 0 0 0. Okay. So if I'm looking at this sphere now, actually this tangent line now no longer is a one line. What happens is now we get actually a tangent. There are many more vectors than which are linearly independent. So there are two vectors which are linearly independent now, not only one vector. So if I want to look at a tangent, it is if I collect all those tangent, what I'm going to get I'm going to get a two-dimensional plane. So I get a tangent plane where u comma v comma w, where AU plus BV plus CV is equal to 0. This is the equation. Again, in this equation, if you look at, this is a perpendicular vector to ABC, where ABC is a vector which is obtained from joining our origin to a point ABC. Okay, so that is what we all of us know. So this is about a sphere, which is a two-dimensional sphere lying inside the R3. Now we can ask ourselves a question: what about the S3? Is there S3? Is there SN there in general, or is there S10 is there? So what should be a S3 is? S3 means, if you look at S3 should lie now. If you look at, if you try to generalize this, S1 is lying inside R2, S2 is lying inside R3. That means if I want to look at S3, it should lie inside R4, right? Or if I look at in general S10, it should lie inside S11. It should lie inside R4, R11. And now we can ask, can we see it now? So because what happens is our eyes, we have what we have is we have our restriction to our line, right? Eyes, we cannot see beyond the 3 dimensions. So if I want to look at a sphere which is in a 3-dimensional sphere lying inside 4 dimension, I can't visualize it because my eye don't allow it. So now the question is whether we really still do we need to kind of review this sphere. But before that, let me look at what we have done it so far for this circle and that of sphere, and then I'll come back to a question whether to study these higher dimensional spheres. Okay, so right now what we did is we consider this circle. This is our circle, and this circle, suppose if I consider right now, I looked at this circle which is lies inside R2, but what I can do is I can look at actually this XY plane lie inside R3 plane. And now if I look at all these points, and if I look at tangents to this plane, everywhere, if I look at these lines which are tangent to this point, what is going to happen is, can you visualize this? Actually, if I put these lines which are tangent to the to each of the point on the circle, so what is going to happen is I'll get something which is a cylinder, right? So I have this circle, and at each of the point in the circle, what I have is I have this line which is perpendicular to this circle. So what I'm going to get it, if I collect all this, if I collect all the tangent lines to the point S, to this circle S1 at a point. So what I'm doing is I'm looking at AB, which is belongs to S1, and I'm collecting them each of these tangents. So what I'm going to do get it, I'm going to get a cylinder, right? So if I look at T of S1, which we call it as a tangent bundle of circle S1, because what is happening is I'm looking at these lines or these vector spaces, and I am binding them together and forming a bundle out of it. So, and these are the tangents, so we call it as a tangent bundle of S1. So if you look at tangent bundle of S1, it looks like a S1 cross R, and it is a cylinder. Okay. Now the same thing we can do it for the S2. So in case of S2, what we are going to do is we are going to tie all these tangent planes together. So that means, what do you mean by tying? Means I'm looking at all the points ABC belongs to S2, and I'm looking at a tangent plane at a point ABC for S2. So this also, if I collect them together, what I'm going to get it is a tangent bundle of S2. I am going to get it. So these spaces are very big spaces. They are no longer a smaller spaces. Okay. So if you look at, for instance, a circle, it is a one-dimensional object, but its tangent plane, which is a cylinder, which is a two-dimensional object. Okay. Similarly, in case of S2 sphere, this is a two-dimensional object, but when I collect all these tangent plane together and tie them together, the tangent bundle which I get, it is going to be a 4-dimensional, no longer 2-dimensional. Okay. So now actually let us try to see whether we can generalize this notion of SN and tangent n plane to the higher order. Okay, so for given any n, can we do it? So that is what actually as a mathematician we try to generalize things together, right? So in this case, let us look at SN. So if you recall what was our definition of a circle was, so we are trying to now generalize it, right? So circle, this is sitting inside R2, S2, this is sitting inside R3. So certainly if I want to look at Sn, where it should contain inside, this should be contained inside Rn plus 1. So that is what we are looking at here. Is there any disturbance? Actually, I'm kind of is there? I'm hearing some echo sound. Is it my computer problem? Or? Yeah. So now let us try to see what is the definition of S1. So if you look at the definition of S1, yeah. So now let us look at what happens if I am taking this S1. So if you look at, remember the definition of S1 is x square plus y square is equal to 1. Definition of S2 was x square plus y square plus z square is equal to 1. So now in order to generalize this, what we are doing is we are looking at x naught, x1, xn, and then you are looking at a summation of I varies from 0 to n of xi, sorry here, xi square to be equal to 1. Okay. So this is a definition of SN, and of course, this is a definition which I am giving. So it should be there. Okay. And if you look at a tangent, what is going to happen for the tangent? If you see in the previous cases, for the circle and so on, what was happening was tangent are the vectors which are perpendicular to uh, our vector, which was given by joining. You take a vector which is 0, 0 and AB, and then look at all the vectors which are perpendicular to AB. So same definition we can generalize. So what they mean by perpendicular means their dot product has to be 0. So if I look at a point A, which is belongs to my Sn, and then if I want to look at what is the tangent plane to tangent n plane to my Sn at a point A is going to be all those vectors which are perpendicular to this vector A. Okay. And if I want to generalize my tangent bundle, I need to take tangent bundle to be equal to all the disjoint union of this tangent plane. So now the question is whether we really do need a higher dimensional sphere. So for that, actually, I'll give you an example of one ant. So what is happening is, suppose one ant which is walking on this, look at a surface. Okay. So this ant which is walking on the surface, and what is happening is, for that ant is while it is walking on this surface, what it will think is, it will think that this is a two-dimensional object, right? Because it can only able to see it on the top of this surface, right? It is only able to visualize this top, and it is walking on this, so it will look like for this ant, this surface is a two-dimension. But nevertheless, suppose if this is a surface of a cube, then what is the dimension of our cube is? It is going to be a three-dimensional object. But only thing is that this ant, since this ant is walking on this surface, it is unable to see the height, the third dimension. So for it, it is a two-dimensional object, but it is actually a three-dimensional object. Same thing is happening with us. We can actually able to see the three dimension. We cannot see beyond it. So now the question is whether our universe lies in the higher dimension. So if it lies in the higher dimension, we do need a sphere which is a higher dimension. And there are some theories which are in the physics. For instance, Einstein's general theory of relativity. It needs fourth dimension, which is Einstein call it as a time to explain the gravity. Or there are these other mathematical theories which came up in early 1950s and so on, which are called the string theory or superstring theory, which tells that we need a 10 dimension to explain the universe. So that universe should have a mathematical consistency. So if you look at this, it looks like it is possible that our universe may lie into the higher dimension. It's just that we are unaware of it. So we, as a mathematician, we cannot stop ourselves to the level just a level which is like a three dimension. We have to go beyond it. And in order to do that, what we need is, we need the equations of this kind of form, so that we don't need to just restrict ourselves to the visualizing thing. We should able to also generalize things using the equations. But this is not exactly the place where algebra comes. Algebra plays even higher role in case of geometry. So let us look at what is the role which algebra is playing for us. Okay. So in algebraic setting, now let us look at this geometric object which we are just now studying. Okay. So there is something called affine plane, which is an algebraic version of a plane. So what is this affine plane is, how it is defined? Let me quickly tell you. So What we do is in algebra, all of you, since you already know what is ring is, so suppose if I have a ring, what we do is in algebra, we look at this new set which we denoted by spec R, and it is consisting of the set of all prime ideas, okay? And then there is something called topology, which is given by Zariski topology, okay? So for time being, let us keep this aside, but let us concentrate on the set. So what is this set is? It is a set consisting of all prime ideals. Okay. So now what are the prime ideals? Prime ideals are like prime numbers. You are MSc students, so many of you know this. So for example, if I take a real number, so real number is a field. So if you look at all the prime ideals inside of a real, they are only going to be there is only one prime ideal, which is a 0. So this is our spec for R. Okay. And similarly, if I take a spec of Z, what are the primes? Primes are generated by the prime numbers. So as we expected, so it is all the ideals which are given by PZ. Okay, but nevertheless, Z is also integral domain. So 0 ideal is always become a prime ideal. So we will have this extra point, which is the 0 point. Okay. So now, so this is what is a definition of specar or affine scheme, what we call. And now I want to explain you, I cannot give in general idea of affine spaces, but I want to give you one example, which is called affine plane. So you can actually able to see how we can give extra information than the usual information in this affine setting. So what is the definition of affine plane is? So if I look at this polynomial Cxy, so what is this polynomial ring is? See, in general, when you study in your graduations and so on, we look at only one variable, right? And what is that variable is x. Generally, we take it as x variable. So we look at a polynomials of this form, right? Where a comma b comma c belongs to R. Here I am writing only a degree 2, but it can be degree can be anything. Any degree polynomials, just what we need is we need it to be a finite degree. So likewise, these are the element of polynomial ring Rx. But now I'm looking at two variables. One is x variable and another is a y variable. So here polynomials are the form, for instance, y square minus b x plus c, or y cube plus xy plus 1. Any of these kind of polynomials. So here how many variables are there? We have a two variables. If you see, if you attended Professor Sujata's talk, she was also talking about the elective curves which were given by the equation y square is equal to x cube, if you remember, and we were trying to find a solution. So these are these kind of polynomials. And if you look at a spec of this is what we call it as a affine plane. Okay, so what is affine plane is? You look at all the prime ideals of this Cxy. That is what is our affine plane. So let us look at what are the points inside this. Since C is an integral domain, Cxy is also going to be integral domain. And whenever we have an integral domain, we always have one ideal, which is a prime ideal, which is a 0 ideal. So this is always there. So this we also call it as a bonus point, okay? Because this is an extra point. Then if you recall, the maximum ideal are always a prime ideal. So what and how maximal ideals are given over here? Suppose if I have a element A and B, these are two complex numbers, then what I'm going to do is I'm going to look at this evaluation map at a evaluation map to C. So what is evaluation map means? Suppose if I have a polynomial in x and y, I'm going to substitute instead of x a and instead of y b. And if I look at, so this map is going to be clearly a surjective map. And if you look at a kernel of this map is going to be ideal. And this ideal, by first isomorphism theorem, I'll get that this is going to be isomorphic to C. And with the Hilbert basis theorem and so on, you can actually show that for here using Taylor series expansion, you can show that this kernel will be consisting of is precisely generated by x minus a and y minus b. And Hilbert basis theorem tells converse also all maximal ideals are of this form. So if you look at here, this is going to be, I'm getting now one-to-one correspondence between the C2. So C cross C. So all the a comma b, I can send it as a xa minus yb. And if I have a maximal ideal, I can send it over here. So these maximal ideal, they have a one-to-one correspondence with your complex plane, which is a C2. Okay. So complex plane means what? It is a two-dimensional complex vector space. So remember that as a real, it is a 4-dimension, but as a complex, it is a 2-dimension. Okay. So these are our maximal ideals, and these are also a traditional point because these are traditional points for the obvious reason, because they are coming from C2. So we already have this extra point, bonus point, which is 0. And now we have all traditional points in the affine plane. But more than that, we'll get something extra. So if you look at this principal ideal, which is generated by f of x comma y, where this f of x comma y is irreducible polynomial. Irreducible polynomials means you cannot factor it into two small polynomials which are smaller degrees. Okay. So if you have an irreducible polynomial and such a polynomial, and you look at ideal generated by it, then these are also going to be a prime ideals, and these are the extra points, and they're like v extra points. Okay. And what are these points are? These are the polynomials which are of the form, for instance, y square minus x cube, or y square minus x cube minus ax plus b minus b, and similarly more of them. And each of this, if you remember our previous sum of the talks, these are precisely the equations which are actually gives us a Riemann surfaces, or torus, which even Professor Arvinda, Professor Sujata, all of them mentioned about this elliptic curves and so on. So now what happened is, in algebra, if I look at a affine plane, it has much more information than that of a usual traditional setting. So what are the extra information I have? First place, I have the zero ideal, which is our bonus point. I have all the traditional points which already I have inside C2. And more than that, I get this extra spectrum of prime ideals, which are not a maximum ideal. These are one-dimensional object. And these are corresponds to Riemann surfaces and so on. So this information is much more valuable than this information is a very valuable information. So when we are looking at the geometric objects in the light of algebra, what we get a much more information. Okay. So this is what is the power of using algebra and geometry together. What is going to happen is, it's actually revealed much more information which is hidden beneath the things which we can't see beyond it. Okay. So that's why it is always important to look at geometry and algebra together. So this is one of the example of why we should study algebra and geometry together. There is another example which let me quickly tell you. This is about this example which you keep on seeing in your graduation and post graduation, which is the relationship between conservative vector fields and Poincare lemma. Okay, so let me quickly go through it. So do you remember what is the conservative vector field, or we call it gradient vector? Sometimes we call it as a gradient vector field also. So it is something which is coming from this gradient of a function f, right? So for such a conservative vector field, what happens? These physics people, in a physics also you use it, in mathematics also we use it. So such a conservative vector fields are very nice because of the following fact. If I have a line integral along any closed curve, what happens to that is 0, right? You must be remembering this fundamental theorem of line integral. And another thing which we know about conservative vector field is curl of this conservative vector fields are 0. So now, if I want to work with a conservative vector field, it becomes much more easier because of this. If I want to calculate calculating integrations becomes much more simple. So now the question is whether converse do hold. Like for example, if I have a curl of f is 0, whether your vector field is conservative. And all of us knows that this answer to this question is not correct, because what is the example which we generally see it? It is inside R2. So you look at R2 minus origin from here. And if you look at a vector field which is given by, so that we call this as a omega to R2, if I give a vector field which is given by x comma y is equal to y divided by x square plus y square and minus x divided by x square plus y square. You can easily check that this for this vector field curl becomes 0, but it is not a conservative vector field. So converse of this theorem is not true, and then whenever it is always good to have a both way theorems. And now we can ask ourselves why this converse is not true, or it is not true for every omega, because here actually I'm considering particular omega which is deleted 1 0. We are making 1 0 in our plane. So suppose if you, so instead of that, what you do is, if you look at your omega to be a solid ball or star-shaped domain or anything which is very nice, which can be what we call it generally as a simply connected domain. In that case, what happens? Converse is also true. That's what Poincaré lemma says. So now actually we can ask, inside R2, my result is true, but if I remove this one point, which is a 0 from this, result is not true. So what goes wrong? So for this, what Poincaré did is, Poincaré was a great mathematician. What he did is, he actually assigned one group to this, all these domains, okay? So he took a domain and he assigned one group, which we call it as a fundamental group. Okay. So for instance, if you look at this solid ball or any convex shape or star shaped domain, then our fundamental group for this it comes out to be identity. But if you look at the same fundamental group for this R2 minus 0, it is no longer a trivial group. It is something which is Z. And this is what is, this group is the one which is, because of which this theorem doesn't hold for R2 minus a point. Okay. So these so this fundamental group is called one of the geometric invariant. Okay. So for every domain, what we do is we assign this algebraic object, in this case fundamental group, and if what we are saying is that if in group certain things is not happening, then it is not going to happen in the geometric setting. So these things are very important for us to give this connection between the geometry and that of groups and or any algebraic objects, so that algebra is abstract things are much more simpler. So what we can say is, if something is not happening in algebraic setting, we are saying here that in geometric setting those things doesn't happen. So such a kind of a connections are very important for the algebra and geometry. Okay. So that is where actually it's this duality theorems comes into a picture, and that is what is our theme of our talk is. So let us see what is this duality theorems are. Okay. So duality theorems means it gives us a connection between this algebra and geometry. Okay. So for example, I don't know whether you heard of this, but Hilbert has given this Hilbert-Nullstellensatz and Zatz, which tells that zero set of polynomials and radical and ideals, they are into one-to-one correspondence. This is very famous theorem and very celebrated theorem. And similarly, there is another theorem which is also a celebrated theorem, which is called Sayre-Swan's theorem. So Sayre is the one who is he's algebraic geometer. He's also a Fields medalist. Swan is also a very big mathematician. He worked on a K theory, and they gave one theorem which gives a relationship between a geometric object, which is vector bundle, which I'm going to talk about, and the projective model, which is algebraic object. So this is algebra and this is a geometry. So these things are giving a connection between this algebra and geometry, and this is very important for all of us. Okay, so when you give any relationship between geometry and algebra, these bridges are very important in studying of greater theorems. So if you look at algebraic geometry, we always study what we do is we study this geometry and algebra together via these kind of theorems. Okay, so these theorems are giving a bridge between joining these two subjects. So what we can do is we can take a result from algebraic setting to that of geometric setting, or from geometry to that of algebra. Okay. So now actually let us look at here. I don't know whether these two words are, both of these are very technical words, vector bundle as well as projective module. Let me explain what is projective modules first, and then I'll explain you what is vector bundle is, and then I'll give you this statement of Sayre-Swan theorem, how it connects this vector bundle with a projective module. Okay. So projective models are, yeah, they are, so let me talk about them. So in vector spaces, what happens, uh, in vector spaces, what we do is, if you have any subspace of a vector space, then what we know is it is again a vector space, right? So like for instance, if I take a line, I know that it is going to be isomorphic to R. Or if I take it complement of this, what happens is, like for example, if I take this line and if I take perpendicular, all the vectors which are perpendicular to this line, that is going to be a plane which is going to be R2, and this line direction with P is going to be R3. Okay, but if I replace, so here in vector spaces means what? They are something over the field, right? So either it will be R or C or Q. But now, suppose if I change the definition of our vector spaces, and I want to define vector spaces over rings, then in that case, what happens is, what we get, it is called modules. Okay. And then these kind of very nice reasons are not true any longer. Okay. So for example, if I take a Z as my ring, and if I look at a module as a Z mod 2Z, okay, so these consisting of only two of these. Okay, so what I can do is I can multiply by Z to Z2. I can add elements of Z2. So this is a module over Z2 is a module over Z. And now if I look at this, it is no longer a free module. That means Z mod 2Z is not going to be isomorphic to Z to the power R, or even more things are also not true. Like you cannot find another module such that their direct sum is going to be free. So it is like here, what happened is, we had this line and then I found another module, another vector space, so that their direct sum becomes free. So that kind of thing I cannot do it. Okay, so this is not true. But the modules with these special properties are called projective modules. So let us give a definition. So let R be a ring. A module P over R is called projective if there exists R module Q such that P direct sum Q is equal to R to the power I. And here this I is called rank of our, so this I, if this I becomes finite, then we say our P to be finitely generated projective model. Okay, so this is a definition of projective model, and these projective models are very important. People have studied it for the very, very long period of time. For example, Sayre's conjecture was that if you have a polynomial ring, whether projective models are they free. For instance, we know that over Z, if you look at all projective models, they become free. So similarly, he asked a question whether modules over this Z, whether they are free or not. And this Sayre conjecture was very famous. Even CMI founder C.S. Sheshadri, he worked on that conjecture for a long time. He proved certain part of that conjecture, and later Quinin and Suslin proved it completely. This study of projective models are very important. So this is a very important algebraic object, and let us relate it with a vector bundle. So vector bundle, we already see the example. I talked about tangent bundle. Tangent bundle is one of the example of vector bundle. So in general, what is vector bundle is? It is a collection of vector spaces. Those are varies in a geometric way over a given base space. Okay, so what is happening is, so if you remember our previous example, I had a circle, and for this circle, what I had was, for every point, I was assigning a line to it, right? So similarly, in general, what is the definition of vector spaces? You have this base space X, and if I take point X, if I take an inverse image of that, that becomes a vector space. Okay, so this X is called base space. This E is called total space, and this pi is called projection. Okay. So here what we are trying to do is, we are looking at this fiber. Fiber means you look at the inverse image of a point. So that fiber is going to be a vector space. Now I'm not specifying my vector space over what field. So it can be over R or over C or any other field also. Okay. So for example, when I looked at this tangent bundle over S1, if you remember, this was, what is this? This was our tangent bundle TS, which was a disjoint union of tangent planes, tangent lines over a point AB. And what we can do is, we can take this projection. Suppose if B belongs to TA, then I can send it to AB. Okay, so this is my map pi, this is my base space, and this is my total space. Similarly, you can look at for the sphere also. Okay, so this is an example of a vector bundle. And once I have this vector bundle, what we can so if you look at here, as I said, tangent bundle, this is an example of vector bundle. So if you look at this, most these objects are very geometric objects. So how to make them algebraic? That is the question we should ask ourselves. So if I want to make them into algebraic setting, that means I have to talk about either modules, or I have to talk about rings or ideals. Any of those terms, they will make it into algebra. Okay. So for that, what we do is, so for instance, I am giving here an example. So what we know about a sphere, for example, sphere is a very smooth manifold, right? You have a very nice maps are there, which are C infinity maps. So if you look at all the smooth maps, which are the scalar field, what is the scalar field means? These are the smooth maps from S2 to that of R. And then what you do is, then you look at these vector fields, which are this, what are the vector field means? For every point on S2, I can assign a one vector inside R3. That is called a vector field. So this, what we can do is, we can multiply this scalar field to the vector field. You might have done all these things into your vector calculus. So because of this, what you have is, we have this V of S2, all the set of vector field. These are going to be a module over this ring of C infinity, this scalar field. Okay, so this is a ring of scalar field. Scalar fields. So this vector field becomes a module over the scalar fields. And then, so now you can look at vector bundles as the studying of these sections. Okay, these are called sections. So now we are looking at a ring, and then we are looking at a module. So we came into a algebraic setting. So vector bundles there is a one-to-one correspondence between this this vector bundle, which is given by base space, total space, and the projection to that of a module and a ring. Little more than this is required, but since I don't have much time, maybe I'll not explain it here. But what we call is sheaf theoretical version, or the algebraic version of vector bundle. This is called locally free sheaf of finite rank. Okay, so locally free is word is for, it is like a free module. Okay, locally free module. So vector bundles in the algebraic setting, if you want to see it, you have to look at them as this vector fields. I mean, it is exactly like a vector fields module over a scalar field, similar to that. Okay. So now what we have is, we have a projective module, which is inside algebra. Then we have this vector bundle, which are in the geometry. And what happened? Sayre in so Swan in 1962, he gave an equivalence between this vector bundle and that of a projective module. Okay. So now this vector bundle, if you look at it, is very geometric concept. So unless and until we have a geometry below, we cannot define it. But then before Swan, Sayre in 1955, he proved for this result for the affine scheme. So what is affine scheme is, just now we saw one example. Anything which is a speck of ring, comma something is called actually affine scheme. So we saw the example of C of xy. And then here you need something called, speck of C of xy, which we saw that affine plane. And to give a geometry on this, we have to define something, ring here, and that ring comes from the C of xy. Let me write one tilde on the top, because it is not just a C of xy, little more than that. So what Swan proved it, Sayre proved it over this affine plane. This is now, he made it into a geometry. So we started with a CXY, and then what happened is, we converted into geometry by giving it that speck of this thing, that make it into a topological space. So from algebra, he took it into a geometry, and once we are in a geometric setting, we can define vector bundles. So once I have a vector bundle, I can come back to them by looking at like this section, like this vector field. We can look at something called the global sections here. So once you do global sections over here, I'm going to come as a module over this ring, and that module is going to be a projective module. So that is what the theorem of Sayre. So what Sayre did it? He gave a relationship between geometry and that of a algebra. Okay, so vector bundle are being connected to a projective model. Similarly, on the similar ground, what Swan did it for the topological, compact topological spaces. And if you look at a continuous function, if you look at vector bundles over those topological spaces, then he also showed the same relation. What he showed it? He showed that vector bundle over topological spaces are same as that of a projective model over the ring of continuous functions. And so this is happening in topology. He did it over algebra, and then later on Foster, he proved the same equivalence for the complex manifold of particular type, which are called Stein spaces. Okay. So he proved it in the geometric setting. So now if you look at our result is just a relationship between vector bundle and that of projective modules. And now we have a 3 different settings are there where actually we can connect them together. So if you generalize this, so what we can do is we can generalize this result using the axiomatic aspect of the problem. So when you do that, what you can do is you can actually go even further. Like for example, right now, whatever I took it, it is in the commutative geometry. But what now we can do it, we can actually generalize it to the much more higher level, which is a non-commutative geometry. So for example, if you look at a super manifold, so in a super manifold setting means what happens is you have something which is in the superstring theory and so on. What happens is we have a commutative part, we have a non-commutative part. And so now can we generalize this problem? So can we study vector bundle over this non-commutative geometry, and can you relate it with the projective models? So what do you mean by relating it to the projective model? So whenever we convert our problems from the geometric setting to that of an abstract setting, what we can do is we can make our problem, we can take it to the really level which is much more higher than that. And people have studied this result. Like for instance, recently me and my collaborator Samir Chavan, we did it for the operator theory also. So what we tried to do is we tried to we tried to study the class of operators for which we can look at eigensheaf, and we try to connect it with a vector bundle. So once you generalize all this geometric aspect to the algebraic setting, we can actually go much beyond it. And the Sayre-Swan theorem is the starting point for that. So this is one of the central theme for the duality between algebra and geometry. Of course, I cannot go into the details of this theorem. I need a little more time for that. And I think I already finished the timing. So maybe I'll just stop now for this about this. But I think what I want to just emphasize that whenever you are looking at a problem in geometry or a problem in algebra, don't look at them separately. Try to see whether you can go from the one aspect algebra and another aspect as a geometry. Try to combine them together. Then what is going to happen is you can achieve the greater results. So with this, I'll stop. But I just want to tell one more thing about since this E-Symposium is about Maryam Mirza Khani. I just would like to read something which one of the book which I have about Mirza Khani. And why I'm trying to read this part is because one of the things about Maryam Mirza Khani was she was not very much interested in mathematics at the beginning of her schooling, and later she became interested after geometry was introduced. So I just want to, since that is particular the theme of my lecture, I just want to read a paragraph from this book, which is called Maryam Magic, to you, so that you can understand how when you combine algebra and geometry together, things becomes nicer. So I'll just read editorial part of this book. So in that it says, as a little girl, Maryam Mirza Khani was spellbound by stories. She loved reading in Tehran's crowded bookstores, and at home she spent hours crafting her own tales on giant roll of paper. Mariam loved school, especially her classes in reading and writing, but she did not like math. Numbers were nowhere near as interesting as a bold, adventurous character she found in books. Until Mariam unexpectedly discovered a new genre of storytelling. In geometry, numbers became shape, each with its own fantastic personality, making every equation a brilliant story waiting to be told. As an adult, Mariam became a professor, inventing new formulas to solve some of the math's most complicated puzzles. And she made a history by becoming the first woman and the first Iranian to win the Fields Medal, mathematics highest award. So with this, I'll stop my lecture. I'm really sorry for the expert because I think my talk will be too easy for them.
Yeah, thank you, madam, for such an informative lecture on algebra. And I thank from the bottom of my heart that you have readily accepted our invitation in spite of your busy schedule. Thank you once again, madam. And next time we'll have full length so that we'll allot you so much of time so that you can finish off. We will again have this lecture so that we will gain some more knowledge on this, madam.
Thanks, sir.
Yeah. Now we'll start our next session. By Professor C.H. Radha, madam, on differential equations.
Hello, I am Megha. Hello.
Good afternoon, madam.
Good afternoon.
I welcome you for this 1 week International E-Symposium, madam. Now I call upon Manisha to introduce today's resource person, Professor C.H. Radha, madam, to you all.
Good afternoon, everyone. I, C.H. Manisha, faculty member of Department of Mathematics and Statistics, RBVRR Women's College. Welcome you all once again, day 5 of 1 week International E-Symposium on Modern Mathematics, organized by the Department of Mathematics and Statistics, RBVRR Women's College. It's my privilege to introduce today's resource person, Professor C.H. Radha Ma'am. Ma'am studied MS Hyderabad. She completed her PhD from Indian Institute of Technology, Bombay in 1994. She was Boy Scout visiting fellow from 1999 to 2000 at University of Edinburgh, UK. She worked as a lecturer in VNIT Nagpur for 9 years. And then ma'am has been reader associate professor and in the Department of Mathematics, and now she is the DC of the organizations. In spite of several honors and distinctions, ma'am is a simple learning mathematics. I request Radha ma'am to take session. Thank you.
Thank you. Are you able to hear me? Excuse me?
Yes, madam.
you-
We can. Yeah.
Oh.
Yes, ma'am.
Can I share my screen now?
Madam, just 2 minutes, madam.
I'm not able to share the screen. I don't know whether there is any problem from this side or that side.
Madam, you can share the screen now as I have made you the co-host.
Yeah. Share.
షేర్ చేయాలి ఫైల్ షేర్ చేయాలా రాసి
రాసేది.
ఫస్ట్ ఇది ఓపెన్ చేయాలి. షేర్ చేయాలి ఇంకా మినిమైజ్ చేసి షేర్ చేస్తాం. ఇది కదా
Are you able to see the screen?
లాగౌట్ అయినట్టుందండి.
No.
Madam, we can't able to see your screen, madam.
Okay.
అది ఓపెన్ చేయండి.
ఏది?
జూమ్ ఓపెన్ చేయండి ఫస్ట్.
Yeah. You put this only.
Madam, below you will be having shared screen, no, madam? You can click that.
Yeah.
ఇప్పుడు వైట్ బోర్డ్ షేర్.
Yeah. Now are you able to see the screen? Yes, please.
Yes, madam. Plain
Okay.
board
Thank you very
we can see.
So, thank you very much for inviting me to deliver a lecture
You
on
are welcome, madam. I think you remembered that you came once to our college to give extension lecture.
Right.
Yeah.
That time probably I gave on B groups. I don't remember what is the topic. What was the topic that I... Do you remember what was the topic at that time?
It's a differential equations only, madam.
Oh, so
Yeah.
this time also it became a differential equation. Okay. So we'll be talking about differential equations. Yes. So differential equation consists of ordinary.
Excuse me, madam. We can't able to see what you are writing, madam. It's a blackboard. We can see. Now we can see, madam. It's differential equations.
Differential equations, it consists of two kinds of differential equations. One is ODE, ordinary differential equations, right? The second one is partial differential equation. Are you able to see? Hello? Are you able to see the screen?
Yes, ma'am.
Okay. See, first I will be talking about the ordinary differential equations. Then we'll move to the partial differential. Okay. So in the partial differential equation, in ordinary differential equations, it is a I mean, all of you know what is an ordinary differential equation. But here I would like to say something else. Probably you would be saying the ordinary differential equation as a relation between independent variable and dependent variable and its derivatives and so on. But same thing, it is whatever I mean, I said that is 100% true. But I would like to interpret it in a different fashion. Suppose I have the curve, so y equal to c into e power x. So as c is varying, I get the different curves, right? As c is varying, I get different curves. Next if as you said that as we are thinking that f is a function of x, y, x, y, y dash, and so on. Again, the derivative of y is equal to g. That's what we think that a differential equation is. But I was about to say that if I take c equal to y equal to c into e power x, that means we get as c is varying, c belongs to a real number. Right? So when c equal to 0, y equal to 0, this is x axis, this is y axis. At when c equal to 1, y equal to e power x, c equal to 2, y equal to 2 into e power x, and so on. As y is c changing, we get it. And we can extend the graphs. So all these curves, I mean, since c is the parameter, I consider all these are belonging to one family. What is that family? Y equal to c into e power x. It is a one parameter family of curves. All these curves in this basket, we are having so many curves, infinite number of curves. One is y equal to e power x, one is equal to 2 into e power x, the y equal to 3 into e power x, like that, say, minus e power x, and so on. Right? So all these curves are, when y is negative, this is not the correct one. When c is negative, this is not the correct one. When c is negative, we'll be having the curves like this. When c is negative, right? So when c is positive, then c is negative, like this. So all these curves are having one common property. What is that property? Is y dash is equal to y. At any point, to take any curve, take any point on the curve, its y coordinate and its slope, they are equal. So what I would like to say is, these one parameter family of curves are represented by a differential equation. Right? So once we know what is the differential equation, then how many types of differential equations are there? You know the degree and order of the differential equation. Now, to say that it is a differential equation, I use the operator L of y is equal to f of x. So in the previous example, y dash minus y equal to 0. So if I want to put this y dash minus y equal to 0 in the form L of y equal to f of x, so L of y is equal to y dash minus y and f of x equal to g. Right? So any differential equation can put it in the operator form. L is an operator. Then a ODE is two types. One is homogeneous and non-homogeneous. Right?
Hello.
Hello?
Hello, Radha.
Huh?
We are unable to see your board. Actually,
Yeah.
after the ODE and PDE, we didn't
After
see.
that, you could not see?
Yeah, we could not see. I'm just writing by what I'm hearing. That's all.
Okay. I'll just. Now, could you say, are you able to see the second screen?
No, madam. Only it is ODE, PDE.
That's all. Okay.
Yeah.
I will. Yes. What about now?
No, madam. Still we can't see.
Yeah, now yes.
Okay.
Now yes.
Right. So this gives a family of flows. The next what I said is I said that we have the two kinds of differential equations. One is homogeneous and the other one is non-homogeneous. So when do we get a differential equation is a homogeneous equation? If y equal to 0 is the solution. If y equal to 0 is the solution, then we say that it is a homogeneous differential equation. If it is not, y equal to 0 is not a solution, then we call them as a non-homogeneous differential equation. Right. Then what do we know about the differential equations? What we know is if we have the differential equation in the form of here y equal to 0 is not a solution because q of x is not appearing, hence it is a non-homogeneous equation. And I wanted to say that when do we say that a differential equation is linear? If L of y is equal to f of x, we talk about only the operators. L of y1 plus y2 is equal to L of y1 plus L of y. Then we call it as a linear differential equation. Whatever may be the order of the differential. So in this case, the L of y is equal to y dash plus p of x into 1. So if you can verify that L of y1 plus y2 is equal to L of y1 plus L of y2, hence it is a linear differential. Linear and non-homogeneous. Okay. Then what do we know about the linear differential equation? Yes, we know the solution in terms of the integral y equal to integral e power minus p dx multiplied by constant plus integral q e power integral p dx. So we feel that we know the solution. In fact, we know in what sense in terms of the integrals. So if you give me p of x and q of x, I will substitute in this and get integrated. Finally, I can say that I know the solution. Right? Okay, if it is not a non-linear equation, linear first order differential equation. So I can write y dash is equal to m of x comma y by n of x comma y. So minus g to g. I'll say that y dash minus m of x comma y divided by n of x comma y. Which, right? So what this same thing we can write as m dx plus n dy is equal to. Now you will able to see that we can talk about the exactness of the differential equation, since it is a first order differential. If it is exact, then if it is exact and m and n are differentiable, so dm by dy is equal to dn by dx, then we say that the given differential equation is exact. Okay, otherwise it is not exact. Then what can we do? Then we can multiply this equation by mu, which is known as the integrating factor, So again, here also we can assume mu is a differentiable function, mu and m, and n all are differentiable functions. So that d by of mu m is equal to d by dx of. So here integrating factors are not unique. It can have infinitely many integrating factors. So even if we can find one integrating factor, we can determine the solution or problem is solved, because our intention is to determine a family of. Now, suppose, then what is the linear and non-linear? What is the difference between linear and non-linear? If we take the linear first order differential equation, it represents one family of curves. If I take the second order linear differential equation, it represents the two parameter family of curves. If I take the nth order linear differential equation, it represents the n parameter family of curves. That means y is equal to a function of x, comma c1, comma c2, comma c3, and comma c. So this is I mean the n parameter family of curves are represented by nth derivative of y plus well, maybe I can put that p1 of x by n minus 1 of x, and so on. P n of x into y. Right? So any nth order, n parameter family of curves are represented by nth order linear ODE. Please remember that. Then what is the difference between linear ODE and non-linear ODE? For non-linear ODE, if I have a first order, I'll repeat. Here the order of the derivative for linear ODE is order of the derivative and the number of parameters involved in the family of curves are equal. If I take the nth order linear ODE, in a general solution, I will be having n parameters. But whereas this property doesn't hold for nonlinear differential. What does it mean? Though I have the first order differential equation, not linear, though I have a first order non-linear differential equation, it can represent more than one parameter family of curves. I'll give one example. Y minus 3 into y dash square plus minus y square minus 2y minus 3 into y dash plus y square minus 3y equal to 2. Y square minus 3y. This has one solution, y is equal to c into e power x. To substitute y equal to c into e power x, this satisfies. It has one parameter family of curves. The second set of parameter curves is y equal to x plus c. If I call this as c1, I'll call this as c3, c2. The third one is y equal. You please can verify y equal to c1 into e power x is the solution of this differential equation. Y equal to x plus c2 is the solution of this differential equation. Y equal to 3 is also. So what is happening? Same differential equation. I mean, we have several two parameter family of course, not a two parameter, one parameter family of course. One is y equal to c1 into e power x. The another one parameter family of course is y equal to x plus c2. And one more solution, y equal to 3. The y equal to 3 neither can be obtained from one y equal to c1 into e power x, or we can obtain y equal to x plus c2. So y equal to 3 is also a separate solution. But this differential equation represents all these three. So for nonlinear equation, for n first order nonlinear equation, nonlinear ordinary differential equation, it can represent more than one parameter family of curves. One parameter family of curves is not one. Like that, we are having several. Several could be more than two. Not only that, there are some special solutions. In this example, y equal to 3 is the one special example. This kind of example is y equal to 3. The solution is known as a singular solution. I mean, having the singular solutions or special solutions and having the more than one parameter family of those for first order nonlinear differential equation is due to the nonlinearity only. Why it is nonlinear? This whole thing, if I call this as L of y, I cannot write L of y 1 plus y2 as L of y1 plus L of y2. I cannot write. Hence, it is a nonlinear differential equation. Right? So, now what we know about the first order differential equation? For nonlinear or for the linear differential equation, yes, we know the solution in the integral form. If it is a nonlinear equation, then there is no guarantee. But first order, first degree differential equation, then we can put using the integrating factor, one can make an attempt to determine the solutions. So that's all we know about the first order differential equation. So what we know very little about the first order differential equation. Then when it comes to the second order differential equation, linear y double dash plus p of x into y dash plus q of x into y is equal to r. For arbitrary values of p of x, q of x, and r of x, can we determine the solution? No. There is no algorithm. There is no theory involved in this. Right? Theories developed to determine the solutions of it. Then what do we know? Instead of p of x, if we have the constants p y dash plus 2y is equal to r, where p, q, and r. Then all of you know that we take y equal to e power x, m satisfies two quadratic equation, hence we get two solutions. So their linear combination is the solution of this differential equation y equal to c1 e power m1x plus c2 e power m2x, where m1 and m2 are solutions of m squared plus p into m plus q into h. And due to this non-homogeneous term, we get a particular solution. Right? This part is it is well-known factor. Then what happens if P of x, capital P of x, capital Q of x, and capital R of x are not constants? Still, we are in the linear second order ODE only, linear. linearity is important. Even if it is linear, we are not able to determine the solutions for arbitrary functions of P of x, Q of x, and R of x. Whereas if it is a first order differential equation for variable coefficient, we are in position to determine this. Right? So that is lost even for when it comes to second order differential. Then what happens if, what happens if P, Q, and R are not constants? Then what do we know? Yes, we know we can make an attempt to solve initial value problems. That means y dash plus P of x into y dash plus Q of x into y is equal to R of x. Initial value problem means y of x naught is known to me and y dash of x naught is also known to me. Y of x naught is equal to alpha, y dash of x naught equal to beta. Then I can make some little effort to find the solution, not for all values of x. If this is the x-axis, x naught is a point on the x-axis, I can determine the solution in a neighborhood of x equal to x. X naught minus delta 2, x naught plus. This is delta, it should be how to determine okay, but even if delta is known, how do we determine the solution? The one solution is using the power series solution, a and x minus x naught whole power. Right? Then here what we are trying to find out the solution in this form, we assume P of x is analytic. We assume Q of x is analytic. We also assume R of x is analytic. So if I pay that much for P, Q, and R, that means if P, Q, and R are analytic, then they can be written as a Taylor series form or Maclaurin series form, so that these ANs can be determined when there is a G. Right? So these constants, the ANs are to be determined such that by substituting in the differential equation, P of x is also analytic, Q of x is also analytic, R of x, and so Y is analytic. So here one can find the power series solution. Now, the radius of convergence in the short series solution is nothing but the interval in which we know the solution. Okay? So only this much is known for the second order linear with variable. For non-linear, we don't know anything. Still we are, right? Are you able to see the screen? Please let me know. Hello?
Yes, we can.
Yes, ma'am.
Okay. So still will be in the linear, but nth order ODE equal to nth order ODE. Nth order by n plus P1 of x into yn minus 1 of x, n minus 1 to the derivative, P2 of x by n minus 2 to the derivative of x, and so on. Finally, we have Pn of x into y. So this is nth order linear differential. You take any nth order linear differential equation that can be written as n system of first order differential. Y double dash. I take the only second derivative, second order differential equation, P of x into y dash, Q of x into y. So how do I write the second order differential equation as a two first order differential equations? Let y is equal to y dash is equal to, right? So that u dash, what is y double dash? Is equal to u dash. So u dash, y double dash is u dash plus p of x into y dash is equal to 3 plus q of x is equal to 2. This is one differential equation. The second differential equation is y dash. So a second order differential equation can be put it as a two first order linear differential. Right? Then what? Similarly, one can write the nth order differential equation in the form of a system of n first order differential equation. Okay, so we'll concentrate on the system of equations. Again, we'll restrict of the system is 2. So y dash is equal to ax plus by. Okay, I will not write again because y dash is equal to alpha 1x plus beta 1y, and z dash is equal to alpha 2x plus beta 2. Sorry. Okay. I'll change the independent variable for convenience sake. I'll write dx by dt is equal to alpha 1 into x plus beta 1 into y, and dy by dt is equal to alpha 2x plus beta. So here the independent variable is t, dependent variables are x and y, right? But the independent variable is not appearing in the right hand side, hence this system is known as autonomous system. So this autonomous system has a peculiar behavior. What is that behavior? Behavior is at t equal to t naught, x is equal to x naught, y is equal to 6. So satisfying these conditions, I have x equal to phi of t and y is equal to psi of t. X equal to phi of t and y equal to x equal to phi. So that means this is satisfied such that x naught is equal to phi of t naught and y naught is equal to psi of t. So what is happening to this? In the xy plane, by eliminating t from x from phi of t and psi of t, I can write y is depending on x. For example, x equal to 2 cos theta, y equal to 2 sin theta. Theta is varying from 0 to 2 pi. So by elimination of theta, what do we get? X square plus y square is equal to 4. Right? So x equal to 2 cos theta, y equal to 2 sin theta is the parameter form. Here the parameter is theta. And when you, as parameter is taking the values, when you identify those points x, y in the xy plane, you get a curve. You get a curve. Right? Similarly, here x equal to phi of t, y equal to psi of t. For a given t, I know x and y. At t equal to t naught, this is x naught comma t. X naught comma phi. Right? Now, as the t varies, suppose the t is equal to t naught plus 1. Then I get x as phi of t1 and y is equal to psi of t. So, as the t is varying, I get a curve in the xy plane passing through x naught comma, passing through x naught comma y. right? So now, but here there is something different, something so I think is important to observe. As the T increases, and this is the T equal to T naught. Now T is varying from T naught greater than T naught. Then if the points are rotated like this, I put that as an arrow. Then I put the arrow. As the T increases, the particles are moving along this curve in this direction. As the T increases from T naught, if the particle is moving like this, I put the naught. So once I know the direction, it remains same for all values. Okay. So here we don't say that there are solutions, we say that there are curves. Now, is there any connection between the ordinary differential equation and first order differential equation and this? Yes, dx by dt is equal to alpha 1 into x plus beta 1 into y. dy by dt is equal to alpha 2 into x plus beta 2 into y. X of T naught is equal to x naught. Y of T naught is equal to. This is the two system of first order differential equation. Whereas you might write dy by dx, which is equal to alpha 2x plus beta 2y divided by alpha 1x plus beta 1. In fact, this is nothing but dy by dt divided by dx by dt. That's all. So by this, we could eliminate we are able to see the differential equation without independent variable t. But in this case, what is the independent variable? X. Right? So now when we try to find the solutions of it, y of x naught is equal to y naught. This also will represent the same curve, whatever the curve I have given. So this curve with the solution of the dy by dx is equal to alpha 2x plus beta 2y divided by alpha 1x plus beta. Right? So these two equations are represented by the same curve, but this one tells us something extra. What is that extra? It gives the direction. Whereas if I draw the solution curve for this, it doesn't tell the any direction. That is the number 1 point. Number 2 point is no two paths, hence the directions, the curves which are having the directions are denoted as paths. No two paths can intersect. That is the second point. For the autonomous linear system, no two paths can intersect. Right? So with these two are the different things. Why no two paths can intersect? If two paths can intersect, at this point there are two different tangents. But the given problem says that it has only unique tangent. What is that? That is a dy by dx. So since there is a unique tangent, no two paths can intersect. Hence, when we look about the dx by dt is equal to alpha 1 into x plus beta 1 into y, and dy by dt is equal to alpha 2 into x plus beta 2. So now this has a one specific behavior. What is that behavior? The solutions can be written as y comma x is equal to some c1 into c2 e power m into x. This m turns out to be the eigenvalue of the matrix alpha 1, beta 1, alpha 2, beta 2. If you know it, that's why I'm not paying attention on it. And c1 comma c2 is the corresponding eigenvector of the matrix here. So if we have the two eigenvectors, I'll call it C11. So the first eigenvector is C11. Second eigenvector is C22. Sorry, C21 and C22 e power m1 m2. Right? As alpha and beta, as the alpha and beta are varying, we get all solutions of the system of equations. Then what is happening here? This, if for all values of alpha and beta, if you try to plot the curves in the xy plane, you can see that x-axis, y-axis. See here, by putting beta is equal to 0, I get that y by constant into x is the solution. Similarly, by putting alpha equal to 0, y by constant is the another solution. So now with this, what happens? Y equal to constant is one solution. This is the one, and y is constant into x is the other solution. The constants are different. This is one solution. So, and this is the other solution. I said that, so if my x naught comma y naught is here, I get the solution curve as this. If my x naught comma y naught is lying on this point, the solution curve is like this, and so on. If my x naught comma y naught is here, then my solution curve, right? Now the interesting point is this solution curve, if you plot it, it will be here only. It cannot. If I call this as the region 1, this is the region 2, this is the region 3, and region 4. If you identify one curve in one region, it remains in that region only. Because, as I said, that to enter into this region, it has to cross this straight line. The crossing the straight line means we have the two tangents at the intersection of the straight line. Hence, there is no possibility, which is not true. Hence, for all values of time t, it will be in that region only. Suppose if y x naught comma y naught is here, then the curve will be in this region. It won't go, it cannot move anyway. Right? So similarly in region 3 and in region 4. So this is very important in identifying the fluid flow problems when we try to mix some solvent. What is happening? If I put a solvent, whether it will be restricted to mix in one region or in the entire region, that is depending on the nature of the fluid. So this is one category. The second category is they rotate. In a spiral manner, it gets rotated, and either it will move away from the origin or towards the origin. If it is moving towards the origin, as a t tends to infinity, then we say that it is an attractor. If it is moving away from the origin, we say that it is a repeller. Right? Now, with this information, for non-linear autonomous system also, one can find the solutions. They are known as stable solutions and unstable solutions. So in the mixing problem, if this is the situation, it gets rotated, the fluid, a solvent gets rotated in the one particular region, and it doesn't get mixed in the entire region. Okay? Now, I think with this, I'll move to PDE. How PDE and ODE, are they connected? In fact, I say that they are connected in up to some extent. Solving PDE is with the help of ODEs. Again, up to some extent. What is that some extent? Now, PDEs can be treated as linear PDEs, semi-linear PDEs, quasi-linear PDEs, and non-linear PDEs. Linear PDE, you know, semi-linear PDE, if the right-hand side, okay, I'll write U is a function of X and Y, then Ux, P as a function of X and Y, Ux, plus Q as a function of X and Y, Uy. Ux, Uy means they are partial derivatives of with respect to of U with respect to X and Y is equal to R of X. So this differential equation, this PDE is a linear PDE. The same thing, P as a function of X comma Y into U plus Q of X comma Y into Uy. Here, right hand side is function of X comma Y comma U, then it is known as semi-linear. Whereas P is a function of X, Y, U, Ux plus Q as a function of X, Y, U, Uy is equal to R of X comma Y comma U. This is the quasi-linear. If PDE doesn't belong to any of these categories, then it is called as a non-linear PDE. Except for non-linear PDEs, the remaining these three kinds of PDEs are to be solved with the help of ODEs. For that, I will try to explain how the PDEs and ODEs are connected. Yeah. So I will take a simple example. Ux plus Uy is equal to 1. You have this one method of solving this using the Lagrangian equation. That is the dx by 1 is equal to 3 by 1 is equal to du by 1. So this is the differential Lagrangian equation that you take to solve the PDE. But I'm not going to tell about the Lagrangian equations. I want to see this differential equation as a ordinary differential equation. PDEs are in terms of ODEs. So, but that is possible if I have U X, when X equal to 0, that means on the X equal to 0, that means X equal to 0 gives Y axis, no? Okay, I will draw the I would like to take the data on the X axis. Again, this is only for convenience sake. That means Y equal to 0. So what my aim is solve this differential equation subject to this. That means what I know the solution. I know the solution on the X axis. When Y equal to 0, you give me U an X value, then at that point I know U. At rest of the means above the X axis, below the X axis, I don't. That is to be determined. Right? So how do we do it? What I would like to do is I try to find a curve. Passing on the X axis. I don't know what is that curve. So this curve, I'll write it as Y is equal to maybe S of small x. What is S of X is not known. Let us see what happened. How do we do? So along this curve, U of X comma, my Y is S of X. What is my aim? My aim is that determining the solution along this curve and not touching the other points. I'm touching only, and my aim is to find the solution of this differential equation U, PDE, on the points of on those points only I wanted to determine U. For one curve only. Rest of the things we'll see later. Right? So on this curve, if my aim is to determine the solution, what is U value U value of the points on the given curve is U of x comma s of x. Right? This I will write as capital U as a function x. Capital U as a function of x. Is it okay? Now, what is my du by dx? Du by dx is d small u by dx, which is nothing but ux plus d small u by dy into dy by dx, which is equal to dx by dx. Okay? If my ds by dx is equal to 1, if my ds by dx is equal to 1, what happens? In that case, it is ux plus uy is equal. So what my aim is, I'm trying to find a curve. I'm trying to find a curve so that solution can be obtained by solving the ODE. Because we are familiar with the ODE. Right? So what is that? So if ds by dx is equal to 1 implies s is equal to x plus some constant. So these that means y is not a curve, y is nothing but a straight line, y equal to x plus c. So I will y equal to x plus c. These are the straight lines. That means what are all these are given by y x plus c, right? What are these curves? All these straight lines, along each straight line, you can be determined by solving the differential equation or the differential equation du by d capital U by d capital U by dx is equal to 1. So you said that I said that we solve the only along one equation. Along one equation, that equation we will say is that y equal to x plus c. This curve intersects the x-axis at some point. Right? And that means when x equal to 0, if the curve is here, the y value when y coordinate is 0. When y coordinate is 0, it intersects the x-axis at certain point. At that point, we know the u value. So u of x naught is equal to f of x naught. With this, capital U is equal to x plus f of x naught minus x naught. This is the solution of the given PDE small ux plus small uy is equal to 1 along the curve y equal to x plus c, where it intersects at x. At rest of the points, I don't know. Only on one curve, we have determined the solution. Now, what about in the rest of the region? Now, take another curve where it intersects. So, we can find the solutions where the curve y equal to x plus c, wherever it intersects the x-axis along those curves, one can determine this. If it doesn't intersect, no, there is no point. There is no possibility. So the curves along which linear, semi-linear, quasi-linear PDEs, writing as a ODEs, Those curves are known as the characteristics. The characteristics. So what are the characteristics in this example? Y equal to x plus c are the characteristics. As c is varying, I'm getting different characteristics. So the characteristic curves are the curves along which the given PDE can be written as a whole. Right? Now, all partial differential equations can be find. No, the answer is not like that. Suppose I have a I will take the same example, ux plus uy is equal to. Yes. This is my curve. Okay, I take this in the curve x, y is equal to. So the view x comma 1 by x is equal to x. Right? If I know the curve like this, I would like to take this one, so minus 1 by x, so I will end this. Right? Minus 1 by x. So I know the solution along this curve. X, y is equal to minus 1. How do I determine? I find a curve where it intersects the given curve along that curve with. But here you see the problem. It intersects the given curve at 2 points. At 2 points. So it may not satisfy. So uniqueness is lost. But the same differential equation, linear differential equation, right? Now in this region, I cannot determine the solution because my curve is intersecting. Characteristics are not intersecting the given data curve. If it doesn't intersect, the data cannot be carried along the characteristics, hence one cannot determine the solution. In that case, it has infinitely many solutions. Right? So the difficulty of the PDE is, even if it is linear, if the given curve where the data is known is not getting intersected by all characteristic curves, then there is no possibility of getting there is no guarantee that we can determine the solution. Even if we determine the solution, the uniqueness can lost. When the uniqueness is guaranteed, if all characteristic curves intersect the given data curve, then the solution exists and is unique. Right? Now a little more complication. Instead of take the linear partial differential equation, if we consider the non-linear, then what happens is the characteristics can intersect. Characteristics, I mean, they start from the initial data, but they intersect at some point. So along this characteristic data, along this characteristic, one data is carried. Along this characteristic data, characteristic curve, the another data is carried. But at this point, these two data are to be incorporated. That means again uniqueness is lost. So whenever this kind of uniqueness is lost for quasi-linear partial differential equation, we introduce something else. That means uniqueness is lost means it becomes a multi-valued function. Whenever there is a multi-valued function, we have to increase the solution space. So what is the solution space till now? We are having the partial differential equation means we are first order. The solution space is the solutions all having the differentiable functions. Means derivatives with respect to x and y should exist. Those now the solution space is to be increased. That means we have to look for the solution which is not even to be differentiable. So if it is not a differentiable, then how can we talk about the as a solution of the partial differential equation? Now the partial differential equation, the origin of the partial differential equation is to be seen. In real life problems, partial differential equations are not the differential equations. They have erased from the integral equations. So when we are talking about the integral equations, the solution need not be a differentiable function. It can be continuous. So hence those solutions are known as a weak solutions. So whenever we increase the complexity of a differential equation, we have to increase the solution space. So by increasing the solution space, we have to decrease the regularity conditions. I hope I have made it clear the connection between the PDEs and ODE. And by connecting them, as I said, that the regularity conditions are reduced. So those are nothing but the discontinuities. If the discontinuities are satisfied by certain property, I'm not telling that property, those solutions are known as shocks. Otherwise, they are discontinuous solutions. This kind of discontinuous solutions are highly used in derived for solving the partial differential equation in our real world. I hope I have made it clear. I'll stop now. If there are any questions, please, you are welcome. Thank you for patiently. Hello, Uma.
Hello.
Could you hear me?
Yeah, we are able to hear. There is some
from this side.
There is some echo coming.
Now there is no echo.
I'll just wait for Shweta to come from lab.
If there are any doubts, please welcome. You are welcome, most welcome. If there are no doubts, I would like to thank organizers for giving me a nice opportunity.
Radha,
hello.
We are just waiting for Shweta to come from lab. She's conducting for the students the same lecture. Your lecture is being viewed there in the lab. I am in the department. She'll come and say a few words. Please stay online.
Manisha.
Thank you, madam, for such an informative session on differential equations.
Thank you.
And thank you for readily accepting our invitation in spite of your busy schedule, madam. Now I call upon Manisha to propose formal vote of thanks.
It is my pleasure to propose vote of thanks on behalf of Department of Mathematics and Statistics, RBVRR Women's College. First of all, I thank today's resource person, Professor C.H. Radha ma'am, for accepting our invitation in spite of your busy schedule, ma'am. I thank our Honorable Secretary, Hyderabad Mahila Vidya Sangam, Professor K. Mutyam Reddy sir, our Secretary cum Correspondent, Professor G. Sudarshan Reddy sir, our Principal, Dr. J. Achita Devi ma'am, for their continuous encouragement and support in organizing such programs. A special thanks to Shweta ma'am for organizing International E-Symposium on Modern Mathematics program. I also extended my thanks to ICT committee for their continuous support for the smooth conduct of the program. Our sincere thanks to all the participants who have attended and make it a grand success. Thank you one and all. Thank you, ma'am.
Thank you each and everyone for patiently listening. And we will join for the next session next day at 3 p.m. tomorrow by Dr. Anuradha Kameshwari Madam on the topic Some Aspects of Number Theory in Public Key Cryptography. Until then, stay safe. Thank you, Madam.
Thank you.